Greetings. So we're going to talk a little bit about routing, um, just as like a introduction. Um, so, all right. So with routing, so what are we trying to accomplish? We're trying to forward packets through a network. So, and this can happen in many different capacities. We mainly want to focus on point-to-point connections. Um, and also like routing on a LAN. So routing that most likely would happen in your organization, like corporate world, whatever. So the basic process is routing happens at layer three. So on the OSI model, and IP addresses play a very key role in the routing process. So they are so IP addresses are used in the routing table, um, and so specifically network addresses are stored there, and network addresses are used to um, aid the router in deciding what the best route is. Um, you know, so when it's forwarding a packet. So when a packet enters a router, the router has to decide what is the best route to forward that packet. Um, what exit interface will it go out? Um, how does it decide that? Well, it uses the routing table. So the routing table is just like a list of network addresses and the corresponding exit interface, which is another way of saying network interface on a router, because the packet is going to exit one of the network interfaces on that router. So you have the network address with the corresponding um, network interface, and so that pretty much is so that's like a high level idea of like a routing table. um, so it just goes through each of the network addresses in the routing table and decides what is the best match, and once it finds the best match it forwards it out the corresponding network interface for that route. And how does it decide what is the best route? Well, it uses the longest prefix match in order to accomplish that. So if you have a network address, let's say it's a /24, you know, um, and it's, I don't know, for sake of simplicity, it's it's like 10.10.10.0 or something like that. And you have a 10.10.10.0 network address in your routing table. Well, that's an exact match, so it's going to go out that corresponding network interface. But if you didn't have 10.10.0, the closest match you had was like 10.10.0.0. But that was the longest like prefix like match. Well, then it's just going to go out like the interface correspond to that network address. Um, because there was no other like better match. That was the longest prefix that matched, and it just so happened that 10.10.0.0, um, let's say that had a prefix of /16. So that's why that came up as like the best match. That's also known as like route summarization. So that's something that we'll talk about later. Um, so and there's different ways you can so a router is going to find like his goal is to find the best path, the shortest path. So it has like multiple like characteristics like things that aid in that process, like such as administrative distance and metrics. And first thing it does is like once it finds a matching route in the routing table, going back to my 10.10.0, um, it well, let's say you had multiple 10.10.10.0s in there, it's going to pick the one that has the best administrative distance. So so that's the way how it chooses between like protocols. So if you have a directly connected route, a directly connected interface that of course has a network address, that one is going to be like the have the highest, like it's going to have the best administrative distance, which is going to be like 0. So directly connected interfaces have an administrative distance of 0. If it's a static route, then it has an AD, administrative distance, of 1. So those are like the most preferred like routes. And then you have like egrip and OSPF. They have their own respective like administrative distances. So it's AD is mainly used to choose between like protocols, and then you get into more like more detail, and that's where metric comes into play, and that's how you choose within the protocol. So if you have multiple routes within a protocol, such as OSPF, or egrip or RIP or whatever, um, it's just gonna choose like the path that has the best metric. So if you have, for instance, RIP uses a metric of hop count. So if it had two 10.10.10.0s in there, it's going to choose the one that has the lowest hop count. So it's the same idea for egrip and OSPF. However, they have different metrics than RIP. And so routers have like different ways of like packet forwarding. A more like legacy way is is using process switching, which relies more on the CPU to find the next hop. It's more it doesn't perform as well as like the other methods, which rely more on cache, which is fast switching. Cache lookups are pretty fast because they they're pretty close to like the order of magnitude that a CPU would be running. Um, so that's going to be pretty quick. And if you want to take it to the next level, you have Cisco Express Forwarding, which has like special tables, a forward information base, and adjacency table. So these are hardware-based tables to speed up lookups, and these are like optimized so that way it can more efficiently do packet forwarding. So the Cisco Express Forwarding is obviously more preferred than the other methods, because it just is able to more efficiently organize like the routing table, so to improve the lookup speeds. So moving along, these are all like basic commands that you'll be using a lot when you're working with routers. So you want to like make sure that when you're setting up a point-to-point connection that you set that you set your IP address or any like router interface for that matter. You're going to like go into global configuration mode and then configure your interface. In this case, we're doing a serial interface, and we just assign an IP address. And when you're done assigning an IP address, you do no shut. The above commands there's a basic commands that we've covered in the past, but these commands are just some basic configurations you can do on your router to set the password, to enable like logins for console and telnet, do some encryption. So you can also down here you have your loopback, so you can define like a loopback interface, and assign an IP address to it. Loopbacks are useful for a lot of times they're used for like router IDs for instance like OSPF. So we'll be going back to that, but this is how you would do it. again, a lot of the configurations that you're going to be doing are going to be done from global configuration mode, and then you just jump into like interface configuration mode. In this case, we're doing interface configuration mode for a loopback interface. Move along here. So we have lots of useful commands that we can do on a router, just like a switch. We are going to store our running config. So we have a running config on a router, and that is going to be whatever configurations we have that are stored in RAM. So your saved configuration is on NVRAM. So if you make any changes, you should back up your running config to the startup config. And as always, you can show the state of your devices using show ipint, show ipint brief, and show run. These are excellent commands to see what configurations you have for your interfaces. So the first two commands are kind of like, they're going to give you the state of your interfaces, whereas show run is going to give you more like what commands were done on your router to configure your interfaces, as well as like how your routing table is configured, and many other commands that you may have done on your router. So when you're doing a serial configuration, so you're doing a point-to-point connection, that's a lot of times serial interfaces you are configured for. You want to see like which side is the DCE and which side is the DTE. So DCE stands for data communications equipment, DTE stands for data terminal equipment, and DCE is the side that does the clocking. So when we connect our two routers together, we're going to use a crossover cable. So one side is going to do the clocking, the DCE side. So so if you had like a CSU DSU cable service unit, data service unit, that is actually going to do the clocking for you. So the router side is going to be the DTE in that particular case. But it's good to get exposure to the clock rate command in any case. So this is a good exercise for you. So when you're configuring your serial interface, make sure you on the DCE side set the clock rate, and you can use a show controllers command with your interface. In this particular case, serial 0. That will tell you which side is the DCE and which side is the DTE. So on the DTE side, you're not gonna do clocking on that side. That's gonna be done on the DCE side, the other router. Okay, so on Ethernet, we instead of a serial interface, you're gonna do a fast Ethernet, or gigabit like interface, and configure your IP address. And just like on a switch, you'll have a bunch of like great troubleshooting and remote control applications at your disposal, such as SSH, traceroute, telnet, etc., ping. So show CDP neighbors, great command, so you can see like what is directly connected to your device, and also to see its capabilities. Is it a switch connected to you? Is it a router, etc.? Also like what platform it's running. So how do you configure? So how do you populate your routing table? Like for starters, you get like a lot of routes for free, depending on like if you configured your network interfaces. If you configured your network interfaces on your router, each of those network interfaces are going to be added to your routing table as directly connected routes. So you get those for free, and they will have an administrative distance of 0. So So what if you want to add like manual routes in there? So in order to do that, you're going to use the IP route command. This is how you add a static route in there, and that will have an administrative distance of 1. So how do we, let's say I wanted to add a route to this particular network, 192.168.10.0, with a subnet mask of 255.255.255.0/24 out serial 1. Well, this is the command I would do, IP route. The IP address or IP address of the network, followed by the subnet mask, followed by the exit interface, the next hop. Similarly, if I want to add a default route. So a default route, what is that? Well, that is like kind of like your gateway on your computer. So you have a Windows computer, or Linux computer, whatever it is. You're going to have this configured a gateway IP address. The gateway IP address is your router, is the router to get out to the rest of the world, like get to other networks. So it's a similar idea with a router. It's the only difference is that a router knows how to get to other networks. But what if you are not able to handle like all those routes? I mean, obviously you can't have every route on the internet on your router. So it has to be able to hand it off to someone that does know about those other routes. That's where our default route comes into play. So if it doesn't know about a route, it's going to go out to the default route. So it's good to configure that, on your router, so that way your users can get out to the internet and get to the rest of the world. So we just do IP route. So we're doing these commands from the global configuration mode. We do IP space route space 0.0.0.0 space 0.0.0.0 space and then the exit interface. In this case, it's S1, so serial 1. So with routing, we have, so obviously like if we have like lots of like networks, this could potentially be a problem because we have to add them all to our routing table. And if we add them all to our so if we're doing this like with static routes like I did on the previous slide, that can be pretty tedious. Doing that by hand. I mean, maybe you like doing it on 1 or 2 routers, like okay, it's not so bad. But what if you had to do that on like a dozen routers or 100 routers? So, and plus there's a lot of room for mistakes too. So that's where like dynamic protocols, routing protocols come into play, because it allows you to like share routing table information with other routers on the network. So there's mainly like 2 different types of like routing protocols. There's distance vector and link state. And distance vector protocols use hops as a metric, and I mentioned that before with RIP, which stands for router information protocol. That is kind of a legacy routing protocol. It's still used today, but it's not as like it's not as scalable as like other routing protocols such as egrep and OSPF, which we'll talk more about. So distance vector use metric of hops, and link state use they take more things into account to calculate the metric. So it's usually a formula that comes into play when calculating the metric. So for instance, OSPF uses like bandwidth to calculate its metric. So and egrep, which is a hybrid routing protocol, it does have some link state properties as well as like distance vector like properties to it. So it has like its own special formula. So distance vector will broadcast all of its like routes at once to its neighbors. So it's like constantly spitting out the routing table, the whole routing table each time. Whereas like link state um, routing protocols, they only like give out the information of like what changed. So distance vector protocols, like they do broadcast to notify other routers of like any updates, and they have a pretty slow convergence times. Whereas link state routing protocols are quicker. They can converge faster and have a more complete idea of the topology. So that's what convergence is. Like when you have a complete idea of the topology of your network, then um, then your routing protocol has converged. So next hop, that is the next router um, that a packet will go out. So if a packet has entered your router knows where to put it because it looked at its routing table, looked it up, found the network address in there, and it knows what the corresponding interface that to send it out. That is the next hop. So passive interfaces is a way to stop broadcasts from being sent out interface. So each routing protocol has the ability to turn this off. RIP, egrip, OSPF. So for instance, you don't want to send out like broadcasts like on a serial link, so that way you don't eat up space with your ISP. So instead of doing like a routing update, you might want to do like some static routes there perhaps. So going back to administrative distance, so here's a little table here. So you have directly connected, like I mentioned, is equal to 0, static route is 1, egrip is 90, OSPF is 110, and RIP is 120. Split horizon is a way to stop routing updates from being sent back to the through the receiving interface. So this is used to prevent routing loops. That's one like trick that sometimes utilized. That has to be utilized. So we talked about metric. It is used to distinguish between what is the best like routing protocol to use. I mean within a routing protocol. Administrative distance is how it chooses the protocol, like which protocol is the best. Including also the static and directly connected routes. But if you do have a route, the same route, which is directly connected as well as being like advertised by egrip or some other routing protocol, it's going to choose to directly connect it because it has the best administrative distance, obviously. 0 is the best. Okay, we will pick up OSPF next time.